Okay, let's get started. We'll continue our discussion on Shannon's coding theorem. So we will complete the proof of the converse coding theorem, and then we'll get into bounds, combinatorial upper bounds and lower bounds on rate versus distance trade-off, more in the Hamming model. That's going to be fun. So let's recap from last time. The statement of last time. The Shannon's converse coding theorem. So what was it? It said give me any BSE channel. So this was just for BSE. Shannon did it in general for any discrete memoryless channel. So you give me any BSE, that is for all P in 0 half. And you give me any epsilon. So such factor you can allow. Said that there exists a delta. I can choose a delta and a n naught, such that for all n greater than or equal to n naught, suppose k is great if k is greater than or equal to 1 minus hp plus epsilon times n. So it's larger than k is more than what the rate says, and E is some encoding function for this k to this n, and D is some decoding function. K union what? Sometimes it just says same. So if k is this, and for all this one, says that because the rate is a bit too large, there will always be some message in the space in which this encoding decoding pair is going to just fail miserably. There exists an m prime, sorry, m in 0, 1 to the k, such that the probability when you pick, so you encode m and then you add noise according to the BSE channel. This noise is picked according to the BSE response, so it will only p to the n, and then you decode this. The probability that it is equal to m will be less than or equal to 2 minus 2. So it's miserably. It's a wordy theorem, but it should be clear what the meaning of the theorem is. It's just a formulation of what we had. And what we see today is the proof of this theorem. So basically, how is the proof of this? We sort of gave an intuition for it. So let's look at it. It's going to be similar to the Hamming bond, packing bond. We're going to say that there are so many, that each message is sort of partitioning the space into so many parts. Each part has considerable volume, and therefore the number of parts can't be too much. So it will violate the K assumption. So to begin with, let's assume for contradiction. That for all m in 0, 1 to the k, we have that this probability DEn plus E equals m. All m recover with non-trivial probability. So the probability is over E. The only probability over here is over E. Let's assume this and we'll get a contradiction at the end of this. So now let's look at the space. Let's consider the ambient space.
So,
yeah,
just for recall, so that probability exactly means that if we take a ball around the M, there will be only M is itself, right? The point, not any other message.
No. So I didn't say ball any such thing. There is some encoding procedure, there is some decoding procedure. No matter which encoding, decoding you give me, this is a specific decoding you are telling me. You could do something in this one. Whichever encoding, decoding you are telling me, I'm going to say it's going to fail. No. For contradiction, I'm assuming that. For contradiction, I'm assuming that, and I'll get the contradiction.
What happens non-negligible probabilities?
Huh? For contradiction, I'm assuming that this is happening with non-negligible probability. And then I will show that if that is false, I'll get a contradiction. Therefore, there will exist a M for which the statement of the final conclusion of the theorem will be. Now, this is the ambient space that the code words are deciding, and the corruption is all happening over here. So I want to say the decoding is going to sort of partition this. Give me any decoding procedure, it's sort of partitioning this space. Because what's the decoding space thing? It takes every point here and it's going to return some message. This one. So the decoding, of course, for some points it could be returning the bot function. So if you consider this, so let's for all m and 0, 1. Okay, let's look at dm. What is dm? dm is the set of y in 0, 1 to the n. So that the decoding, when you apply it to y, it returns n. So it's that part of the space which decodes to the message n. So this is sort of, if you look at it, this is dm1, dm2, is dm3. It's sort of going to cover the space. I do not know how it's covering it, but it is all I'm claiming is the key observation is the dm's are disjoint by definition. And that's all I will use about the decoding process. That this is similar to what we had there. We had these nice balls of radius d minus 1 by 2 around every code word, and they were disjoint because of the distance property. The same thing is true over here. The only property we use is these things are disjoint. So that's the key property I'm going to be using. DMs are disjoint. Now, how can we, given this, if DMs are disjoint, how did the other proof, Hamming proof, go? We said that each DM is of a particular mass, and there were so many DMs. There are 2 to the k DMs, we know that. If the product of this has to be less than or equal to 2 power n, and if k is large, this will be a contradiction. So if we knew the size of each DM, if a lower bound on the size of each DM, then we would be done. Question is, do we have a lower bound on the size of each DM? And I want to say we don't have a lower bound on the size of each DM. What do we have? So the question I want to ask is, do we have a lower bound? On size of each DM. I want to say, what do we have by assumption? By assumption, we have the following. By assumption, for all m, we have that probability. If you pick a e in the space, em plus e is in dm is greater than or equal to 2 power minus delta. That's the assumption we have. So dm contains, so equivalently I can write this in the following, or that is probability over e E belongs to Pm minus Em. What I mean by minus is every string you go and just subtract out. You do the bitwise, you XOR it with Em. That's all I'm saying. So we know that we don't have a lower bound on the size of dm, but we have a lower bound on the measure of dm in this sense. And so from this I would like to infer a lower bound on dm. What's one way of inferring a lower bound? Okay, you have this, how do you infer a lower bound?
Fraction of e. Telling you the fraction of e that will be, I mean, for each such e, you are going to get a point in dm, right?
So yeah, for every such e, you're going to get a point in dm. So it's basically, so you take each of you take all the strings in dm. For each of them, you have to look at the corresponding e's probability, add them up. That is exactly this quantity. So one way of getting a lower bound of this is each of the e's happen with sufficient probability, large enough probability. Then the size of dm is at least this by that minimum minimum or maximum, which should I put? The minimum probability, the maximum probability.
It gives that it gives a measure of dm minus e, right?
Yeah.
That bound.
It gives a measure of dm minus e, but in this measure, what I want is the size measure. There are two different measures we are talking on dm minus em has the same size as dm.
What exactly is dm minus em?
dm minus em is just, so when I give you a set minus x, this is the set of all y minus x, y belongs to x. That's all. Thank you. That's the most natural thing. Okay. Not use the minus notation. Let's just use, because it's binary. Let's just make it plus b plus e. It's all the same.
So basically, that is implied by the probability over e, that e belongs to dm equals to the power dm.
Yeah.
That simply means that.
Which one?
From the d plus em.
Yeah.
It simply means that probability of e belongs to dm over e is at least
What over e?
is
Saying probability over e is the randomness.
Yeah.
And this theta equals to the power delta minus delta.
Yes.
So, and you want that from there, I somehow want to transfer it to some volume bound. Right?
I want to, so there are two different notions of measure on dm minus em, dm plus em over here. One is according to this measure, which is coming from the Bernoulli Pm distribution. And then there's the other, which is the size measure, the number of points. I want to go from one to another.
So thanks to the law of large numbers, when m is large enough, let's consider the volume of E restricted to those who is having a life.
Yeah, so you're jumping one step ahead. So what I want to say, suppose you had a bound on the largest probability in this, then this is suppose the largest probability of E was a particular thing, then this is just that P max, this is less than or equal to P max into the size of dm. Or if it's the smallest probability, it's P min into size of dm, and that min will give you. Now the P min, I want to have a bound on it. So that's why the reason you're going for P min is because they can, if you're not a typical guy, P min and P max, this can be really tiny. So I will choose, so what we now do is we will choose the shell. Well, once again, we go for the shell. What is shell? The shell is exactly Sm, which is set of all y in set of all y in 0, 1 to the n. This is exactly what Peja was saying. That is, y belongs to a ball around em with what I want it to be, p plus epsilon n minus the ball em p minus epsilon n. So basically Sm is just this quantity. Okay, follow what I mean. So Yes, that's Sm, and these are that's Em, and it's this shell. And what do we know? What do we know? We know probability that E. Probability that Em plus E. Actually, I don't have to do it for Sm. Maybe just have done it. That's fine. Probability Em plus E is not in Sm. What is this? Huh?
So this is the channel.
This is a Chernoff one. This is at most 2 power minus some C epsilon square. Chernoff one. And now I want to now go back to, I want to say probability E plus Em belongs to Dm. Dm intersection Sm. So is it both belongs to Dm and the typical? This is what Sridhar was saying. What's the typical? So what can it be? It is at least 2 power minus delta n. At most, how much can you be shaving off? You can be shaving off C epsilon square. So this quantity is at least 2 power minus delta n minus 2 power minus C epsilon square n for all n. Okay. But now we are in sort of good shape. Now I want to say, on the other hand, what do I want to say? Probability of E plus Em. This is the probability only over E. It's in Dm intersection Sm is less than or equal to P max times the size of Dm intersection Sm. And what is P max? P max is just the maximum probability of E in Dm intersection Sm minus Em plus Em of this form of the probability of E coming under the Bernoulli machine. What is this quantity? So I want to put an upper bound on P max. What's an upper bound on P max that I can put? So that I can, from this I will then I can get a lower bound on Dm intersection. Huh? So firstly I want to say this is certainly less than or equal to max P belong to P plus P minus epsilon n to P plus epsilon n P power d 1 minus P power n minus d. Because these are all the possible guys that could have come, and I'm just taking the max over this. What's the max over this? So which is the guy which actually obtains the maximum value in this range? Huh? Is that true? So let's write this again. Let's write PD 1 minus P n minus d. This is nothing but P by 1 minus P to the power d into 1 minus P to the power n. Fair enough. This is a fixed quantity. T doesn't change. This quantity, what's this number? This is a number less than 1 because P is less than half. Therefore, this is maximized when D is as small as possible. And that's why we sort of chose the shell. Therefore, this, so I want to claim because of this. Because of this, this is less than or equal. This is less than or equal to P to the power 1 minus P minus epsilon times n 1 minus P to the power n minus P minus epsilon n since okay. So that's this one. So let's go back to our this one. Therefore, we have that Dm. Therefore, for all m, Dm intersection Sm is at least 2 power minus delta n minus delta n by p power p minus epsilon n 1 minus p power n minus p minus epsilon. All right. So I have got a lower bound on the size of dm. This is what I wanted. I wanted a lower bound on the size of dm, that I could not. So, but dm intersection, this is still a lower bound on the size of dm. This is a number which is sort of familiar to us. So let's write it down in terms of things which we know. This is 2 power minus delta n. This is p power pn. 1 minus p power 1 minus pn. The terms remaining are, there's a p power epsilon n which goes to the numerator, and there's a 1 minus p power epsilon n which is in the denominator.
So there should be the subtraction of
Sorry, there is a subtraction of minus 2c. So what I will do right now is I'm just going to assume that this is, if then, so I will assume that this quantity is say minus, of which direction do I need it? So I will assume it's less than 2 delta prime m, where delta prime m is just, so I assume this quantity is just half of this. So it's direction 2 delta m. If there's a suitable choice for large enough n, I will choose, because delta is our choice. We have, if you look at the theorem, we have to choose. There's an epsilon and I choose delta, so I will choose delta to be large enough so that this number, that 2 power minus c epsilon square, is insignificant compared to minus 2 delta. So is that we have this. So now we will return. So what do we know? We know that 2 power n is less than or equal to summation m size of dm, which is less than or equal to summation m dm intersection sm. It's certainly that also. The dm's intersection sm also are disjoint. And this one is what? What is this?
Let's contain the D part.
Huh?
Sorry, what am I saying? So it goes the right direction. But n is greater than or equal to, that's what I have written previously. It's good enough. dm intersection sm. And this is what? This is greater than or equal to summation m 2 power minus delta n. This is 2 power minus h p of n. That's exactly what I had, times p 1 minus p epsilon n. So this is exactly equal to 2 power k minus hp of n minus n. There's a 2 delta. There is a plus epsilon log 1 minus p by p, that is 1 by p minus 1. This all gets out.
Now, if k was larger than this quantity, you run into a contradiction. And that's exactly the delta is chosen such that this is k is larger than this quantity. If k is larger than n into 1 minus hp minus 2 delta plus epsilon log 1 by p minus 1, then contradiction. It's the same. Yeah, it's almost it's very same spirit as the backing bound. It's just showing that if you have a decoding function that's a partition or almost it's a disjoint almost a partition of it, separates the ambient space into two parquet locations. And if you have a bound on the size of each two parquet, then you can get a bound of the number of such distinct objects you have. It's very much similar in the spirit. The only difficulty was we don't directly have a bound on the size of this. We only have a bound on the, according to the Bernoulli measure. Then we use the typicality of this one to get from that move to the bound on the size. That's the entire. Okay. That's the end of one. Yeah, so with that we'll conclude our discussion on Shannon versus Shannon's model. So let's just, so concluding, I want to compare Shannon versus Hamming. The first and most important difference, both of them were trying to model this transmission or communication. Shannon tried to model it using in a probabilistic sense. The modeling was, so the modeling is in a probabilistic sense. Whereas this was in terms of worst case number of errors. And that's with respect to model. With code, Shannon really actually never talked about the code per se. He talks of it in terms of encoding and decoding process. He gives E and D in terms of E and D. That's how the code is specified as the image of E. Whereas here actually Hamming actually gave an explicit code, and E and D were defined in a probabilistic sense. They were not, and this is a different probabilistic than the probabilistic. This is the modeling of the channel. This he showed that in the good case there exists a E, and the E he didn't give an explicit E. He just constructed show that a random E works. So it was not an explicit construction, whereas Hamming actually gave an explicit code C. He actually never talked about E. He never talked about E, but he did talk about D implicitly in the sense he told you how to do the decoding in the worst case. So he also did give the decoding was also explicit in some sense. He actually gave out an algorithm, which was that's whatever it was. This is actually the main key difference between Shannon and Hamming. Most of all, this one, because we will be actually focusing on very explicit codes and their construction and algorithmic process, we will most of the time focus on Hamming. Every now and then we will see how some of these code constructions actually do imply certain things in the Shannon model. So that's the primary difference between these two. It's how Shannon and Hamming differ in the modeling, and then how they come up with the code. Shannon shows there exists a code, and then he gives strong impossibility results about can't happen. Hamming explicitly comes up with the code, and for that code he demonstrates that that's the best code. So both of them gave positive and negative results for their specific this one. Shannon is far more general in terms of what sort of communication you can do, because he thought of every channel. He thought of Hamming's talked about very specific channels and this one, but the general spirit of Hamming is try to talk about worst case number of errors. You can now talk of it in a more general sense. Okay, so with that we conclude our discussion on the Hamming and Shannon models, and now go back to return to our Hamming model and ask about rate versus distance trade-offs. So return to the Hamming model. What we'll do in this lecture and the next is sort of rate versus distance trade-off. This is vector. And notice that that's primarily because the code, we will call a code C, as code C was specified by, there were 4 different parameters in the Q. Okay? And our question was, give me which, I tell you 4 numbers, N, K, D, and Q, 4 positive integers. Is there a code with, that has these? Right now, there's only one, this one, K should be less than or equal to N, D should be less than or equal to N. That's the only requirement. Which possibility of these 4 are feasible? That's the question we want to ask. So ideally, I would like to draw sort of this 4-dimensional space, and I'm saying these points are feasible, these points are infeasible. This is what I want to talk about trade-off. It's going to be hard to visualize the space, so we will focus on, we will reduce the space to 2 dimensions. So the way we will do it is, firstly, we will fix the alphabet. We will think of alphabet, say Q being 2. We will talk about, whenever I write this theorem, we can think of, we will say what's the corresponding version for larger Q, but we'll fix the alphabet to be some alphabet. So most likely it will almost always be Q equals 2. Then, instead of looking at N, K, and D, we look at the fractional K and the fractional D. Fractional K is exactly rate, fractional D is fractional distance delta. So these are the 2 things we have. So we are more asking it in an asymptotic sense. We are not asking it in a specific K and D. We are asking, is there a family of codes which have this particular rate and which this particular fractional distance? I don't care if there's one specific code that has it. What I want is there exists a family of codes. That is, as N goes larger and larger, I must have a code which has that particular R as rate and that particular distance as delta. So we will look at R, which is K over N, and delta, which is D over N, and say 6. Typically. So, and our typical response are going to be of the following type. What we'll be proving is, so this is delta. I can almost straight, I can never draw a straight line. Well, I mean, I never draw, my angles are always skewed. We are drawing this R versus delta plot. And I want to ask which of these points are feasible points. So the sort of theorems which we will be proving is the following. That is, there will be some curve like this, such that notice that once something is infeasible, everything above it is also infeasible, because that's actually does better than it. So these, so once we show a particular point is infeasible, everything to the top and to the right of it is infeasible, because that's a better code than it. So what we are going to be doing is we are going to say, we are going to be drawing these red lines, taking that everything above the red line is infeasible. And we want the red, and similarly, we are going to, so these will be sort of impossibility results. This will be upper bound, so upper bounds on, this will be impossibility results. You can't achieve better than this. And then we'll actually give code constructions, and then we'll draw curves like this. It states that I will actually construct a code with this parameter. Notice once you construct a code with this parameter, you have codes everything below it, because that's this code performs better than it. So this is sort of, this is downward closed, that is upward closed. And ideally, I would like to come up with a line which says you can achieve everything up to this line and everything above that line you can't achieve. This is something which we do not yet know. And over the next 2 lectures, this lecture and next, we'll come with various curves which are going to be approaching each other, but there's still actually a large gap between these 2 curves. So this will be the feasible region. This will be the infeasible region. Here is D. This is the gray area where I can.
So we know these graph will be convex. We know these graph will be convex.
Whether these lines are convex, the optimal, it's not clear whether they are convex. All the plots I will draw will actually, curves which we will obtain will be convex, but I don't see why it should be convex. The optimal things why it should be convex. Yeah, because I only know this way. I don't know if these 2 points are achieved. I do not know why everything in between along them should be achieved. I don't know. I don't see it off the top of my head why you're convexity. Basically, you're stating that this curve should be convex like this. That is, if 2 things are achieved here, everything in between should also be achieved. I don't see a reason why that should be.
No, because if I was doing the instruction here, there was a reason.
It's hard thing on the distance which is not there. In Shannon model, it's not, there's no hard distance.
So the
In the Shannon thing, there is no R. There is the Shannon doesn't talk about.
Yeah, because it's Shannon model.
Hmm?
There it is.
There it is. Yeah. Here I don't see it. I don't know.
The meeting is going in the region.
Huh?
The meeting is still going in the Monsoon.
Why? Because it says that.
Just below the green.
Huh?
That's odd because now I'm. Let's see, if it ends, we will restart.
Sir, so the region where it is visible,
Mm-hmm.
is closed or it might be like you might not. Is there any case where you cannot achieve any curve, but you can go towards the curve where it is not feasible, but you can put approach towards that slowly and slowly. So means from where you are guided that there might be means if you are getting a curve here, then it is a closed region.
By the way, the bottom line is the bottom line, the green line, we are going to show it today. The green achievability is what's the one of the bounds, the Gilbert-Varshamov bound, which we will show and we will actually show. And that has not changed since the 60s or so. It's the red one which has been coming lower and lower. The feasible region, we will hopefully by the end of this lecture, if not next lecture, we will exactly draw one curve and we will show that every point on that curve is actually achieved. Every point on that curve is achieved. And that has been the fixed line since the 60s. That curve has, so it's strongly believed that what that green line is also the red line. This is so that's going to be the plan for the next, this rest of this lecture. The next lecture, we are going to be coming up with red and green curves. In fact, green curve, there will be one fixed green curve which we'll do by the end of this lecture. The red curve will keep coming lower and lower. And in fact, the assumption is, and the belief is, the green curve which we have is the best curve. The red is the one which we don't. But this is, I don't know if we have a justification for the okay. What I thought of is we call the Hamming bound. Right, but it's actually an impossibility. What was the Hamming bound? The Hamming bound was the following statement. It states that the mod C had to be less than or equal to q power n into volume over the q-sized alphabet of ball of what radius? Huh? D minus 1. D minus 1 by 2. We entered in terms of T error correcting, but in terms of distance, it is floor D minus 1 by 2. Okay, this is what we have. This was the one. I want to now rewrite all of this in terms of R and delta. So rewriting in terms of R and delta. What is the left hand side? That just becomes q power kn. That's the number of the code words. This is less than or equal to q power n. We need to put a bound on this. So recall from last time, we had this claim. This is where the binary entropy function came. For all p in 0 to half, we had shown that volume 2 npn is bounded above by 2 to the hpn, and this is also almost applied minus little o1. We've proven this. There's almost an identical bound for similarly for
for larger Q. This was for the binary alphabet. We can do a similar thing. Only thing is that I have to define the notion of the query entropy function. I can define a query entropy function. The query entropy function is this. So we have a similar statement for all P which is less than 0, and half gets replaced by 1 minus 1 over Q. There was a place in the proof over here in this bound where we actually used P is less than half. The proof, if you recall, there's a place where we needed to know that P by 1 minus P was less than 1. And a similar place will come here. So we will show almost an identical statement that wall Q and Pn will be less than Q power HQPn, the corresponding HQP minus the low one, and where HQP is defined very similar to this one. It's P log Q to the 1 base 1 over P plus 1 minus P log Q to the 1 by 1 minus T. So this is almost generalized, but there will be one more term to this which we didn't have there. P log Q minus 1 is we have this one extra term. In the case for Q being 2, this is contributes 0. We didn't have, and this is primarily because if you recall the volume Q and T function, recall for binary it was just n choose j going from 0 to t. But for this one it has this Q minus 1 per g. If you recall the volume one, it had this Q minus 1, and that's the reason why this will sort of come up. All of this. This was just to go back to this. I want to write this in terms of this object. So I want an upper bound on 1 by volume. So I'll take the lower bound on volume from this. So you will get that this is Q power H HQP minus the low one. That is K is less than or equal to okay. So R. Sorry, this I made a mess. This is not Q. This is just Q power K, which is Rn. It's not Kn, it is Rn. It's Q power K, which is Rn. So now if I just look at this, is an equality on the exponents now. And the exponents you can divide by n completely because n is a common this one. So you get that is R is less than or equal to 1 minus H. This is not P. This is not distance, it's distance by 2. B minus 1 by 2. So we get HQ delta by 2 minus the 2. So what I'm claiming is the Hamming bound in the asymptotic sense COVID modeling, I get confused with asymptotic and asymptomatic. We have this R plus HQ of delta by 2 is less than or equal to 1 minus the 2. So basically 1. That's a number. As n going to vanishing, this is going on. Therefore, R, this is the sort of relation. R and delta cannot. If you choose a particular R, delta has bounded distance, and this is true for all. Fine. So this is what I will call. This is the first of the curves which we have. let's plot this curve. That's delta, that's R. Okay, so we have to know what that's like. So let's plot it for Q being equal to 2. Let's take the binary entropy function. Okay. So when R is 0, what does it say? What's the bound you can give on delta? It says h of delta by 2 is at most 1. That is, the binary entropy function should be at most 1. This is sort of is true. Therefore, basically, you can get to this. The bound here is at this, basically that point. So now, so sorry, the bound here is this point. R is 0. It says it's basically, notice anyhow this whole curve is only between 0, 1. It's between the unit square. So it says this bound is over here. And similarly, when delta is 0. When delta is 0, the binary entropy function is 0, 2. So R can go all the way up to 1. So basically, you're saying if there's no distance, you can pack, the code word can be every single thing. Therefore, at least the curve, the two ends are basically the two corresponding, it's 1, 0 over here and 0, 1 over here. And it happens to be this sort of a curve here. You can draw the binary entropy function. It happens to be a concave. So that's this is the Hamming curve. It says basically everything above it is not achievable. Okay, now let's go on to this is a negative result. Now let's go on to what can we do. How can we build a code with good distance and rate? So what's the way in which you can build a code?
If you pick converse and even that can be.
Pick code runner, we'll do even something even more simple. What do we want of the codes? We want the codes to be of distance d apart. Let's just take a ball, pick an arbitrary thing, call it the first code word. Now, this just eliminates everything in radius d around it. So just eliminate that. Now pick anything else from the space. Once you put that, it eliminates another d size ball around it. Actually, a d minus 1 size ball around it. So keep doing this process as long as you can keep doing it. So how do we construct the code with, right? So this is what Gilbert and Varshamov answered, but they did two different ways. How do we construct? So, given a delta, how do we construct? The code with as large R as possible. And of course, there are two ways of doing it. One is what Neha said, probabilistically. We see both of them. Yeah. What? I hope it saved it. Probabilistically. And we'll actually see both of these constructions. So let's start with let's start with even simpler. Let's start with the greedy construction. So let's actually give a procedure for it to be a very inefficient procedure. So what's the thing? You initialize the code to be the empty set. You initialize a set of possible things to be everything. And it goes while S potential code words which you can pick is not empty. Pick an X in S arbitrarily. Set C to C union X, add that. Now you have to reduce S. So S you sort of take out the ball of radius b minus 1 around X. So that's prohibited area. You keep doing this. That's a while loop. So that's the greedy construction. We just keep on doing it. Certainly by design, so let's fix n. So how is it going? You're given a delta, So you're given n and delta to begin this process. Given n and b, which is thinking of it as delta n. So by design, the distance of C, the actual distance of C, delta of C is greater than input. That's by construction. We just need to ask how many code words, what's the process done this. So how do we question is what's the rate of what is sizes? At the end, I want to take at the end of process. If you draw a ball around the code of p minus 1, take the code word points, and what I mean by this, take the code word points and on each one of them put a ball of p minus 1 and take the union of that. What should that be? Huh? That should be the whole space. This should exactly be 0, 1 to the end. Because otherwise I would have, the process would have gone for one more. So we do know this. That is 2 power n is equal to size of b, c, b minus 1. Yeah.
What if there is some space like, but it's not enough to put a
So you don't need to put a ball, no? When you take a point, you know that that point is far away from everything else. Because that's a bad, yeah, because it's, you don't need to put a ball. When you pick an X, you don't need to put an X, you only need a point because you know it's far away from everything. But once you put an X, a whole ball around it is eliminated. So what do we know about this guy? This guy is certainly less than or equal to size of C times the volume of the ND minus 1 ball. Right? That's just an upper bound. By the way, I should write everything more generally to power n. Let me stick to it. I could have done this more generally for Q, but the same thing. All good. So what is this? So this one you get that size of C is at least 2 power n times volume 2 ND minus 1. So what this tells you is explicit. It gives you an inefficient construction. This construction runs in time exponential in n. You have to search the whole space. It's not poly in n, it's exponential n. But it gives you a code. For every choice of n and d, I give you a code which has this property. Okay. So that's the actually, this is Gilbert's code. Let's translate this to rewriting in the asymptotic sense. Rewriting in terms of Rn delta. What will we have? So you have on the right, you have 2 power Rn is greater than or equal to 2 power n. And here I want a upper bound on volume, which is just 2 power Hp. Here it will be H delta. So that is R plus H delta.
So in particular, it says, I give you a delta. There always exists a code whose rate is at least 1 minus H2 delta. Okay.
So that's back to this one. And this is what is called the Gilbert. This is what called the Gilbert-Varshamov. This is Gilbert's bound. Varshamov does so. Varshamov and Gilbert proved things independently. Gilbert gave a greedy construction. Varshamov actually, we'll see what Varshamov does. This is the construction where, and let's look at where this curve is. Where this curve is. So how do you? Let's look at the extreme points again. If an R is 0. What? Huh? R is 0, delta can go up to which point? It says H2 of delta should be, it can be go all the way to 1. So delta can go to half. Half is this one. So actually, if you look at this curve is going to, it will be so this is the red one. Red one, which we noticed was the line R plus H2 delta by 2 equals 1. That curve. This is the green one. It's going to be the curve R plus H2 delta equals. It says for every point on this is achievable. And this is at this point it's important to notice. This is half. Okay. Thus, this is what's called the GB. Okay. So I only said what Gilbert did. What did Varshamov do? So now, okay, so this says there's a code with this nice property, but this is sort of similar to Shannon in the sense that just gives a code, and it is not how do I work with this code? This code is not. So can I give more structure to this code? Particular one structure which you can ask is it a linear code? So then it at least has a small description for it, it has a generic description. So what Varshamov showed is actually this is also attained by linear codes. A random linear code or a greedy linear code will also get this problem. So Varshamov's result is the Gilbert bound is also achieved by linear codes. That is the statement of the question. Together these are called, and it's called the Gilbert-Varshamov point. We will see this. How much time do I have? I have enough time. So I will prove. I will actually give another construction, not a greedy construction. We will actually do a show that a linear code also achieves this problem. This is where we are clear. the theorem which we are going to prove is actually this predicted jointly with Gilbert-Varshamov. So let me prove the theorem, then let's come to. Once again, there are, how do you construct this linear code? There's a greedy method, there's a probabilistic method. For the arbitrary code, we can show that the greedy method works. The probabilistic method almost works actually for an arbitrary for Gilbert form. You can pick a random code with that rate and check if it is one. So if you do the proofs, it will not work. If you pick a random code, it doesn't work. You have to drop off a few code words and then it will. So this will actually go as a problem set. I will say random code will not satisfy Gilbert's form, really works one. But once you drop off a few code words, then it will satisfy the Gilbert form. But in the probabilistic sense, actually, so that's in the arbitrary code. For a linear code, actually, both the random and greedy satisfy the construction. So because we did greedy over there, I will give a probabilistic construction of it. So linear code, I'm going to give a linear code. We give a, there's once again both the probabilistic and there's a greedy. So we will do this in class. This possibly in the problem set. That is, you can be over here. This is what in class we did. This not true exactly, but can be fixed, modified to attain that modification. So, what I want to show, so there are multiple ways. You can pick either the parity check matrix randomly or the generator matrix randomly and show that the corresponding code is this one. Both actually work. Parity check gives a little, I think it gives a little better parameter, but let's generator matrix is easier proof, so we will do so the probabilistic construction of linear codes. Linear codes. So let's just pick G, which is generator matrix as an n cross k matrix. Random. That is each entry. Each of the nk entries are picked IID from the uniform. The Bernoulli half dispersion. Okay. So that's the generator matrix. We pick this generator matrix. I have to show that there's a particular choice of K for which this will work. What do we want to show? So now we have to, and now comes look at the code C, which is given by G of X, X in 0, 1. That's the code. What we want to show is, we want to show two things. Firstly, want to show that the rate of the dimension of the code, the dimension of C is K. More precisely, we have to show that all the all the columns of the code are linearly independent. And furthermore, we now have to show the distance of the code, distance of C is at least. We show this for a particular choice of okay, you choose K to be not too large for which this will happen. Okay, so I give you D and I will choose K to be a particular. We actually do both of these things. So that's what we want to do. So clear? So how do we go about doing it? So basically we are looking at GX and we want to ask. So let's let's for instance, let's fix the x 0, 1, k, which is not the all zero string, that is a non-zero x. You can ask what is the probability. So firstly, what can you say about x? So what's the distribution of g of x? Huh? It's a uniform because it's a linear combination of k different this one, and it's a non-zero linear combination because x is non-zero. There's at least one of them which is completely random, and that is enough to make g of x be a perfectly uniform sample from 0, 1 to the end. So gx is distributed uniformly on 0, 1 to the end. This is for, and it's important that this is non-zero x. Okay. Hence, from this, what can you say? What is the probability that the weight of gx is smaller than d? So the random choice is over g, not over x. X is fixed. I fixed x. So what is the probability that this happens? So it's a volume of a d minus 1 ball by 2 power n. It is exactly volume of n d minus 1 by 2 power n. What do we care for? We care that probability there exists a x, there exists a non-zero x such that weight of g of x is less than d. Because even if one of them exists, then the code has distance less than d. So just do the union form. This is certainly less than or equal to 2 power k minus 1. I'm going to drop that 2 power k minus 1, just keep 2 power k. It's 2 power k into volume n d minus 1 to power. Now, if k is chosen small enough, then this number can be made to be less than that. And that small, exactly, we know exactly what the value is. If you recall, I want, if k is less than n minus htn, then this is actually going to be, then you're going to have less than 1. And hence, did I make a mistake? Yeah, then I made mistakes. Therefore, there exists a g for which every non-zero guy is always of distance greater than or equal to. Once this is less than 1, so because of that, there exists a g for which every guy has distance large and you're in good shape. In fact, you can exactly bound this, but you know exactly what the value of this. You can say it's not just there exists a g, most g. You can, depending on what this problem, that's the probability of error. Everything other than this every g other than this is actually going to be a good g for us. So all those will have large weight. So what I have shown in this case is that the code has good distance. What about dimension of the code? This is I want to claim this is a statement we have to learn. If we choose, so this is the statement which we have over here. We've proven this fact.
They all have large unit, at least b unit.
Yeah. That they can't. So they can't be a zero linear combination of them. So if they have to be full rank, because otherwise they will be a zero linear combination of them. So this statement actually proves both those bullets over there. It proves actually the Hamming weight is large, and it also proves that they cannot be a non-zero linear combination of these guys. So if take any x which is non-zero, not only is the combination non-zero, there is no linear combination, it also has to have at least a distance b. So you're proving both of these in one shot over there. So this is Varshamov's construction. It says that, in other words, that is with high probability a random G such that K is less than n minus HPN is the generator matrix of the NK.
And that is exactly the same thing which came about in the Gilbert book. Varshamov bound is a little more in this one, nicer than Gilbert. Gilbert gave a greedy construction. Varshamov showed that code has more structure to it. It's a linear code, and furthermore, it's not just a linear code. Almost all linear codes are going to have this property. Once the only bad property is that once you drive that to as small, that's the error property. What's in brief? That is small, random code is good. So of course, this tells you that you can the good codes, the number of codes that lie on the Gilbert-Varshamov bound are abundant. Most codes have this property. What I want is an explicit code. Can you give me an explicit code? And we still don't know how to answer this question. This is open. We know that a random code has this property. We don't know of any explicit binary code that goes on the above the GB code. For the few instances where we've been successful, if you go for codes not over the binary alphabet, over some alphabet of size 49 or something, there are these algebraic geometric codes which do happen to fall above the GB code, just above the GB code. That's the only thing we know. Otherwise, every other construction falls below the GB bound, and we don't yet know how to achieve explicitly a code that falls on the GB. And by the way, notice that this is just an achievability factor. There might be, in principle, potentially there can be codes which are well above the GB bound but below the Hamming bound and stuff. Forget it. We don't know of any explicit codes even touching this green line. And there have been sort of papers which will say, take a particular point on the green line and say I can come up with codes arbitrarily close to that point. Forget the whole thing. Even that is, in fact, that won the best paper award in stock a couple of years ago. This was the construction of epsilon by stretch with Tashma. It was just take a point with on this GV bound, take a particular point, and was able to show constructions of explicit codes coming arbitrarily close to it, but still not on the curve. Okay, so we have this picture here. So this is
it is not true that the perspective.
so it's conjectured. It is so. By the way, then the algebraic geometry it is teeny bit above this thing. So you can have a similar. So it's certainly false because I have these algebraic geometry codes. In fact, over a fixed alphabet is alphabet size 49 or something. You pop these called the Gopa codes which do achieve this. They slightly beat the new one. So in CS construction, there are very few examples of things in which there's an explicit construction which beats a random object. One are these Gopa codes, these algebraic geometric codes. They beat the GV bound, which can be got by a probabilistic construction. The other is there is this construction of expander graph due to Loboski, Phillips, and Sarna, which does better than what it has slightly better expansion than what. But in terms of spectral gap than what a random graph achieves. It gets better than that. To my knowledge, these are the only two constructions. There are the LTC constructions, which random will fail completely, but then we have explicit constructions. So to my knowledge, among the code in the coding world, almost always you say a random code has this property and you want to achieve it, and almost never we've been able to achieve it. They're just these three specific cases where we've been able to beat the random code. In most other cases, we have not even achieved the random code. So we have many a time we'll draw these sort of green curves which show this is with respect to R and delta, with some other property will show a random code achieves this property, and then the goal will be to get an explicit code which achieves this property. In fact, a large part of this course will be exactly to even construct a code. So far we haven't yet constructed a code which has positive constant rate and constant delta. So that's just a point somewhere here. So every code that the Hamming code which we get, the rate as you go for n goes to the rate is 0. It goes to 0. The Hamming code delta is 0, so it lies at that point, that end. Then we'll talk about some other thing called the Hadamard code, which will lie at this point. The rate. What was I saying? So on this curve, there will be we'll construct another explicit code called the Hadamard code, which will actually lie at this point. We haven't yet constructed a code so far, this one, and a large part of the course will actually need to construct a code over here. Anywhere in this which has delta bounded away from 0, r bounded away from 0. That's all we want. That's called a good code. And furthermore, once we have that, we would like to go all the way to the green curve, which we don't yet know how to. More things which come more closer and closer to it, we don't have explicit codes on the curve. So it's from the explicit construction point, it's a big open problem to construct codes over the binary alphabet that will come as